This is AP Calculus 115, and we are going to connect horizontal asymptotes with limits as x approaches infinity. And in order to do this, we need to first review horizontal asymptotes. We've hinted at this before, but I want to make sure you understand where our horizontal asymptotes come from when we're graphing polynomial functions. So to find horizontal asymptotes, it all has to do with the degrees of the numerators and the denominators in your polynomial function. So if your degree of the top is equal to the degree of the bottom, remember degree is the highest power of the exponents. So if the degree of the top equals the degree of the bottom, for example, like it is right here, then our horizontal asymptote will be y equals the ratio of the leading coefficients. So if you look over here, we do have an asymptote or horizontal asymptote here because the degrees are the same. If the degrees are the same, your horizontal asymptote will be y equals, and it's the ratio of the two coefficients of the numerator and denominator. So the ratio here, the coefficient here is 2, the coefficient here is 2, so 2 over 2 is 1. So y equals 1 will be the horizontal asymptote of that function. Moving on to another type of horizontal asymptote, if the degree of the top or the numerator is less than the degree of the bottom or the denominator, the degree on top is less than the degree on the bottom. So this is x to the first, this is x squared. So this degree is lower than this degree. Then your horizontal asymptote will always be y equals 0. It will be the x-axis there. And then here, if the degree of the top is greater than the degree of the bottom, like we have in this situation where we have this is to the degree of 1, this is to the degree of 0, then that will not have any horizontal asymptotes. And there's going to be a connection between these horizontal asymptotes and the limit as these functions approach infinity. So that's what we're going to talk about next. So next I've got some examples where we're going to talk about the graphs. We're going to talk about how to find limits of these graphs as x approaches infinity. We're going to make some connections between what those graphs look like, what the limits are, and what the horizontal asymptotes were that we found. So if you look at this one, it's asking us here to find the limit as x approaches infinity. So they give us a function, f of x equals 2x, and then they ask us to find the limit as x approaches infinity. Well, looking at that function, I know I'm going to have a vertical asymptote at x equals 0 if I set the denominator equal to 0. And then I also know that since the degree of the top is less than the degree of the bottom, I have a horizontal asymptote at y equals 0. Okay? So we have those asymptotes, so we know that our results for this function is going to be in here somewhere. And I could graph it. If I plug in 1, I get 1/2. If I plug in 2, I get 1/4. Plug in 3, I get 1/6. So it looks like as it approaches infinity, my graph is doing this. It's approaching my asymptote. And then if I move to the left, if I plug in -1, I'll get -1/2, -2, -1/4. So it appears that on this side, it's approaching the asymptote in that direction. Okay. Now this is asking me for the limit as x approaches infinity. Well, if I look at that, as x approaches infinity, as x moves toward the right, it looks to me like that's approaching 0. So that would be my limit as x approaches infinity. Now, think about that. What did we say the horizontal asymptote was? Wasn't the horizontal asymptote y equals 0? Okay, let's look at the next one. For this one, if we were to graph that, my horizontal asymptote, since they have the same degree, my horizontal asymptote would be y equals 1/2 because it's the ratio of the leading coefficients. So y equals 1/2 is my horizontal asymptote. I could graph that. I'm going to have a horizontal asymptote at 1/2. I'm going to have a vertical asymptote at 0. With this one, honestly, if I were going to graph it, I would put it in my calculator because you're dealing with a fraction horizontal asymptote. That's just going to be a lot of work if you do it by hand. But we're going to have other options as well. If you think about it, When we first started doing limits, we said that the easiest way to do a limit was to plug the number that x is approaching into the function. Well, we're still allowed to do that here. If we plug infinity in, we would have infinity over infinity. Isn't that really the same thing as g of x equals 1/2? Because the x squared and the x squared are both going to cancel out, okay? So if that's the case, g of x equals 1/2, well, isn't the limit as x approaches infinity for this going to be 1/2? Wasn't that one of our properties? Okay, so plugging numbers in still works here. We can plug infinity into the equation and still get the answer. Let's do that here. If I plug infinity in as 1, as we have 1 over 2 times infinity, well, if the number on the denominator is getting larger and larger and larger, doesn't that mean this entire fraction is approaching 0? It's getting smaller and smaller? Because if you think about it, if we plug 1 in, we'd have 1/2. 2 would give us 1/4. 3 would be 1/6. 4 would be 1/8. 5 1/10. 6 1/12. 7 1/14. 8 1/16. Those numbers are getting smaller and smaller and smaller as we plug in. So we know as we plug infinity in, we're approaching 0, something closer and closer and closer to 0. Hopefully you're making a connection here. Our horizontal asymptote is going to be equal to our answer as x approaches infinity. Now don't get that confused. It has to be approaching infinity for that to work. If it's not approaching infinity, if it's approaching another number, then we have to look at it the traditional way and plug that number in, not infinity. Look at this one. If we plug infinity in here, infinity plus 1 is infinity. If we have infinity over 3, isn't that just infinity? As infinity gets bigger and bigger and bigger, it doesn't matter if we're dividing it by 3, it's still getting bigger and bigger and bigger, larger and larger. So our limit here is going to be infinity. Now think about the horizontal asymptote for that. The degree on top is higher than the degree on bottom. It has no horizontal asymptote. So essentially we could say it has no limit per se other than infinity. We don't have a decisive number that is, but we do know it's getting bigger and bigger. And you could graph that as well to see that that is the limit. In this section, I'm going to give you several different examples, and I'm going to show you some different methods of solving these that become significant as we move forward. For some of them, the horizontal asymptote thing is going to work, and you're going to be able to get your limit with no problem. But the first thing I would do with all of these is plug infinity in first, see if you get an indeterminate form. If you do, then you're going to have to do a little bit more work to find the answer. So if I do this one, if I plug infinity in, infinity to the 6th would be infinity, times 9 still infinity, minus infinity is still infinity, over infinity. So we end up with the indeterminate form infinity over infinity for this one here. So in order to do this, and if you think about this one, there is no horizontal asymptote here. We cannot find the horizontal asymptote because that only applies to polynomial function. This one has a square root in it. Square roots are going to make this a little bit more difficult. So I'm going to have to try to figure out a way to get this so that it's something that is workable, okay? Plugging in infinity didn't work. So I'm going to have to find some way to be able to simplify this so that I can get it into a different form, still equivalent to what I've got, but looks different. First of all, I notice the top is underneath a square root and the bottom is not. It would be very helpful if the top and bottom were both under a square root so that I have something that I can plug numbers into and get some decisive answers with. So that's what I'm going to do first. I'm going to force the bottom to be underneath a square root so that I can simplify this whole thing a little bit. So in order to do that, now I'm going to write this limit as x approaches infinity one time. I'm not going to keep writing it in my entire problem. It becomes redundant. So we know at the end, once we get this thing simplified, we are going to plug infinity back in for x, okay? So that still applies. We will do that at the end. I'm going to make sure I can get the top and the bottom underneath a square root. Well, if you think about this, if I square, well, let me write that. If I square the bottom, I've changed the value of it, but if I square it and put it underneath a square root, Now isn't it the same thing that I started with? Okay, so I've made it look different, but it didn't change its value. And that's very important as we're dealing with this stuff. Now that I've done that, isn't that the same thing as having that entire fraction underneath the square root? We haven't done anything that changes the value of that fraction. We've just made it look different. Now, couldn't I FOIL this? That would be x to the 6th plus 2x cubed plus 1. Once I get it here, if I try to plug infinity in, I'm still going to have infinity over infinity. So I still have the indeterminate form. So I need to figure out a way to simplify the numerator and denominator so that I'm not changing the value of that function. There is something that we can do here. You're going to hear me in class, if you have me in class, saying divide by the highest power of x. Okay? If you divide by the highest power of x on the numerator and the denominator, you then can get things simplified a little bit easier. And so dividing by the highest power of x on the numerator and denominator is essentially the same thing as multiplying by 1. And let me show you how. On the top, we have 9x to the 6th minus x. And on the bottom, we have x to the 6th plus 2x cubed plus 1. Now, if you look at that, the highest power of the x is x to the 6th. I want to divide everything in this fraction by x to the 6th. So I want to divide the top by x to the 6th and the bottom by x to the 6th. Now, if you think about that, isn't dividing by something the same as multiplying by its reciprocal? If I multiply the top by 1 over x to the 6th, and I multiply the bottom by 1 over x to the 6th, isn't that the same thing as dividing the top by x to the 6th and the bottom by x to the 6th? Okay? Essentially, I'm just multiplying by 1 if I divide the top and bottom by the highest power of x. So if I do that, and I'll show you every step. Now you may be able to skip some of these steps, but I'm just going to show you everything. The top would be 9x to the 6th minus x over x to the 6th. And the bottom would be x to the 6th plus 2x cubed plus 1 over x to the 6th. And now I'm going to simplify. I'm going to take the x to the 6th and I'm going to put it into each of the parts of the numerator separately. So each term in the numerator is going to get divided by that bottom number or bottom variable separately. So when I do that, if I look at this one, 9x to the 6th divided by x to the 6th is 9. Minus x divided by x to the 6th is 1 over x to the 5th. That's my new numerator. This one, x to the 6th divided by x to the 6th is 1, plus 2x cubed over x to the 6th is 2 over x cubed. 1 over x to the 6th is 1 over x to the 6th. Now that whole thing is still underneath the radical. Now, I have divided everything by x to the 6th. I have not changed the value of this fraction. It's still the same, it just looks very different. Now, we are trying to find the limit as x approaches infinity. Well, look at what we have here. This looks very different. It looks like something that maybe I could plug infinity into now. So let's do that. If I plug infinity here, well, that's still 9 minus, well, 1 over infinity. That's going to be 0. That's approaching 0. So that's going to cancel out and give me 0 for that limit. I have a 1. 2 over infinity approaches 0. 1 over infinity approaches 0. So look at what I have. I have 9 over 1. I have the square root of 9. The square root of 9 is 3. So as x approaches infinity, I will get 3. Looking at this one, if I plug negative infinity in for x here, negative infinity squared will be positive infinity. Negative infinity squared will be positive infinity. So we'll have a positive infinity over positive infinity. So that's still the indeterminate form. So we're going to have to do something different. It's not factorable, so there's nothing that will factor to cancel out. So if here I divide by the higher power of x, or I multiply by 1 over x squared, which is the highest power of x, we've really just multiplied by 1. So in doing that, what I would end up with is x squared over x squared plus 4 over x squared. And then you would simplify it from there. So this is just really working on your algebra skills. The thing about calculus is, the calculus is not hard. Calculus is really fairly easy, but the algebra associated with calculus is what makes the course difficult. So if you're struggling with your algebra skills, that's what's going to make calculus difficult for you, okay? So as we get to these things, I will try to explain the algebra as we go through, because I know sometimes it's been a while since you took algebra, so you might be struggling with those type of things. So with this, if I go ahead and divide that, x squared over x squared, well, that's just 1. And then I divide this into each individual term. X squared over x squared is 1 plus 4 over x squared. Well, now if I plug infinity or negative infinity in, negative infinity squared is infinity. So 4 over infinity approaches 0. So this part approaches 0. So we end up with 1 over 1, which is 1. Well, let's look at the horizontal asymptote. The degrees were the same. If the degree is the same, it's the y equals the ratio of the leading coefficients. Leading coefficients, 1 over 1 is 1. So in this case, the horizontal asymptote aspect would have worked, but we did get the indeterminate form at first. So you have to investigate that to make sure it does in fact work. Okay? For this one, the limit as x approaches infinity. If we just do direct substitution, we've got infinity on top, we've got infinity on the bottom, so we've got the indeterminate form. If we look at the horizontal asymptote, that would be y equals 1/4. So let's see if in fact we get 1/4. All right, I'm going to go straight through and divide by the highest power of x on the top and the bottom. Understand that's the same thing as multiplying by 1 over the highest power on top and bottom. Okay, it's the same thing as multiplying by 1. But I'm just going to go directly in and divide all 3 of these by x cubed. So on the top, I would have x cubed plus 2x plus 1 divided by x cubed. And on the bottom, I have 4x cubed minus 2x squared plus 9 all over x cubed. And then I simplify each of those separately. So x cubed over x cubed is 1, plus 2x over x cubed is 2 over x squared, plus 1 over x cubed, over 4x cubed over x cubed is 4, minus 2x squared over x cubed is 2 over x, and 9 over x cubed. Now, if I plug infinity in for all of the x's, well, look at what happens here. I've got 1 plus, that approaches 0, that approaches 0, 4 minus, that approaches 0, and that approaches 0. So we've got 1 plus 0 is 1, over 4 minus 0 plus 0 is 4. Our limit there, 1/4.